Okay. Yes, now. Now. Good afternoon to all of you and welcome uh, to these courses, Advances in Welding and Joining Technologies. So this is the second live interaction for this particular course, and I think very few have raised the queries. Once I just look into the Google Sheet. So we'll try to discuss that whatever you raise the queries in the Google Sheet. And I hope till now you are enjoying these particular courses. And of course, I have given some assignment also. And you are trying to solve this assignment and with the full concentration and maybe associated with a very specific problem in welding and joining technologies. I hope you are learning, you already learned something, but till you have queries, you can raise also during the live interaction session. First, I'd like to finish this presentation, which is based on the queries raised by you only. After that, maybe you can put your questions in during the live chat box, and I'll try to answer to all of you. So first question you raised this thing, please explain the Rosenthal's 3D equation and also explain how to calculate the heat flow, temperature gradient, cooling rate, etc. with the numerical. And of course, I will be doing that and also explain how to calculate the residual stress in welded joint with the numerical. Please discuss the assignment questions, especially the numericals. So I think there are so many assignment questions and we have already said the solution. Better, I think you can look into the if it is not shared with you till now, finally we'll be sharing the solution also. So at the point of time, there will be discussion on the numericals associated with the assignment. But all assignments, any questions, this is not out of the syllabus or whatever I share I don't know whether you got the PPTs or class notes associated with each and every module. So if you go through each module carefully, you'll get the answer of all the questions what we have raised in the assignment. But anyway, I'm trying to focus on the basic concept or maybe understanding this particular subject, specifically in the Rosenthal's 3D equation. And the second question raised that why these advanced welding techniques are not being used in industries as similar to that of our conventional welding process. Anyway, I'll come back to this particular question, but let's first look into this particular first question, the Rosenthal's equation. So once when you try to do the finding the solution of that, we always do that analytical solution of the temperature distribution by solving the heat conduction equation. So this is the very basic general equation and not only applicable for welding problem. It is any kind of the heat transfer problem. This we normally solve the heat conduction equation. So I have written the three-dimensional heat conduction equation here, and maybe if you look into the dimensionality of this particular equation, that is representing each and every term is a per unit volume. So here the most critical part is that Q dot. Q dot indicates the internal heat generation per unit volume, or maybe that represents that heat generation rate of the heat generation per unit volume. So maybe I can say like that it can be watt per meter cube, like in SI unit. So that will be the unit for the Q dot. And of course, the similar kind of units on the other terms. But it's a three-dimensional equation. Now, if you solve it, there are different ways to solve this particular heat conduction equation. Now, if you want to get this equation, if you try to solve it, and you know how to solve the differential equation also. But not all the kind of the differential equation can be solved analytically, or direct solution you may not get. So in that case, you go for the numerical solution. For example, we normally use the finite element, finite volume, finite difference, this kind of the numerical techniques to solve these equations. But till I mentioned here that analytical solution of temperature distribution. So of course, this heat conduction equation is possible to solve, but you need to do lots of assumptions. With this particular assumption, you will get some analytical solution of this particular equation. For example, I'm just trying to explain the different assumptions, and based on that, what solution we can expect. For example, first I assume that infinite body. In that case, the effect of the boundary condition can be neglected. For example, the figure shows that it's a three-dimensional domain where you are interested to solve the temperature distribution associated with the welding problem. So that is our interest, because the governing equation indicates that variable is the temperature. Finally, if you solve it, you will get the distribution of the temperature. That means temperature in terms of the other, that is in terms of, it can be in terms of space and time domain. You will get the solution of that. So if you try to do that, then infinite body means that all x, y, and z direction, we are assuming that this the workpiece is basically infinitely long along this particular three perpendicular direction. So in that case, you can neglect the effect of the boundary condition, not necessarily to boundary condition, because you are assuming it's infinitely long. This is one assumption. Second assumption is that you are representing the q dot, the application of the heat, because on the domain you apply the heat, and based on that you'll be getting some temperature distribution. So application of the heats here in the form of a as a point heat source. So one particular point you are applying releasing the amount of the energy, and once you release the amount of the energy, and after in a transient problem, you'll be getting the temperature distribution in the whole domain. And other assumption is that initial temperature, basically initial temperature be or reference temperature, you can say, or ambient temperature, assuming that as a zero. With all these three assumptions, you are getting the solution of this particular heat conduction equation. T R is the space, basically R equal to the radial distance in terms of the x, y, and z variable, x square plus square root of x square plus y square plus z square. And it's as well as the function of time also. So then Q by rho Cp 4 pi alpha T by 3 by 2 exponential minus R square by 4 alpha T. So this is the solution of this particular equation. Now, how to derive all this, and that is not going that much of details. This standard solution available in any kind of any heat transfer problem or heat transfer book. So, but with these assumptions, specific to the welding problem, we can get the temperature distribution as a function of space and time. This is the expression. But here you can see that Q actually represents the, here this Q is represents the, it represents the total applied power, basically in terms of the watt you can represent. Rho is the density, Cp is the specific heat of the material, and alpha is the thermal diffusivity, and alpha is basically equal to K by rho Cp. And sorry, in this case, I think alpha is the thermal conductivity. Sorry, alpha here we representing thermal conductivity, and R square by 4 alpha T. So space, temperature, thermal conductivity, time, specific heat, and density, all are the variables, and that represents the temperature distribution. But if you look into the nature of the equation, the solution, it actually indicates the isotherm contours. It's basically a series of the sphere with the radius r. It means that one particular it will get the temperature in the form of a isotherm contour that is represented in the form of a sphere. So one particular temperature will get one isotherm, one particular radius, and another isotherm means, say, for example, melting temperature, solidus temperature, liquidus temperature, and even more than that, all basically represent in the form of a sphere in this particular domain. So if you try to see the distribution of the temperature, so this is one kind of the solution we can get with this particular assumption. Now if we change it, now if the infinite body, the effect of boundary condition can be neglected, is another case. But here instead of the point heat source, we are assuming the instantaneous line heat source. That means the application of the heat over a line. So that means you are representing the power per unit length. That is the input to the domain. But in this case, we'll be getting the two-dimensional temperature distribution, and initial temperature also 0. With this assumption, we'll get the solution of the heat conduction equation and the TRT in terms of the other parameters. But here you can see R equal to in terms of the x square plus y square. So that means two-dimensional temperature distribution will be getting here. Now, if you look into the nature of the equation, basically isotherm contour is the series of the cylinder. So over the cylindrical shape, this isotherm contour represents the constitute one kind of the cylinder. So that is the solution domain solution we are getting with this particular assumption. Now there is another case. Suppose you are assuming the heat source is not as a point or line heat source. Rather, if you are assuming the plane heat source, then heat is applied flux over a plane. In that case, we'll get the output in the form of a one-dimensional temperature distribution. So in one-dimensional temperature distribution, you are getting this is the expression, and isotherm contours is basically a series of planes. So here, but remember that once we are heat input, basically in we are changing the heat input point to line to plane. All these cases you are getting your temperature distribution. The first case it was the three-dimensional. Second case you are getting the temperature two-dimensional, and third case you are getting the temperature in the one-dimensional case. So these are the actually. You can ask why for the instantaneous plane heat source we are not getting 3D temperature distribution, because the nature of the equation itself will not able to get the analytical solution of the equation if you represent the heat input to the domain in the form of a plane heat source. So that's where getting so to comply with the certain kind of the analytical solution, we need to go for some kind of the assumptions. So that is the one case, but all these cases, it's you're getting the temperature distribution as a function of the time. It means that is a transient temperature distribution you are getting. So that temperature varying with respect to time. So it's analogous to the kind of the spot welding process where you are neglecting or you are not considering the effect of the weld velocity. But if you consider the effect of the weld velocity, then nature of the solution can be different. For example, the analytical solution of the temperature distribution in case of the moving point heat source. That means heat source is the point, but it is moving on a semi-infinite body. It means that semi-infinite body means since the heat source is moving one particular direction, but other two direction is infinitely long. We are assuming that with these assumptions, we are getting the Rosenthal's equations, and that is in the steady state heat flow equations. We are getting this particular solution. But apart from these things, we are other assumptions also they are associated with this solution. One is the point heat source, and we are neglecting the heat losses from the boundary. That is one assumption. Second, you are getting the two-dimensional heat flow in the welding of the thin sheets of infinite width. Now, in practical, the welding plate having some finite thickness. If you consider that thickness, then you will be able to get the two-dimensional heat flow. And infinite width means the other dimension, not the thickness direction, the width direction. You are assuming your workpiece domain is infinitely long. And third dimension, one particular direction, the heat is moving. So in that cases, you are assuming there is a finite, because that is the already heat that the welding torch or maybe laser is basically moving in this particular direction. So here you'll get this particular solution, but in this solution, if you say there is a V, X, H, all these parameters, thermal conductivity, thermal conductivity also there, and alpha is the thermal diffusivity also there, alpha term also there here. Along the x-axis with velocity V, and here V and X we have written. X is coming because the heat source is moving along x-axis. If heat source is moving along y-axis, then we can replace X with Y like that. And V is the velocity, R is the radial distance from the origin, and R is itself as a function of X and Y. So R is the radial distance. That's why we can represent the square root of X square plus Y square. And K0 is the modified Bessel functions of the second kind and the zero order. So this is the solution of this analytical solution of the heat conduction equation with these particular assumptions and by considering the effect of the welding velocity. Now, if we do the other cases also, moving point heat source on a semi-infinite body, but here also application of the heat flux as in the form of a point heat source, and it's on a semi-infinite body. In this case, assuming there is no heat losses, then the solution of the temperature will be like that: T equal to T0 plus Q by twice pi Kr, V velocity, R is there, radial distance, X also there, and alpha thermal diffusivity, K by rho Cp. So this is the in this case also heat source is moving along x-axis. That's why here you can see the values x variable is there, and this solution and r equal to radial distance, but radial distance we are getting the radial distance from the origin. So r also is we can represent in the form of x square root of x square plus y square plus z square. And if you see the solution here, we are not considering we see that it is independent of the time. So this is basically steady state solution, or sometimes we can say in case of not exactly steady state, we can say the quasi steady state solution we are getting in a welding problem. But one difficulty is there, the singularity problem at the origin of the coordinate system. That is the caused by the point heat source assumption. So that means you will not be able to get the values calculate exactly at the point where there is the application of the heat source and point heat source. And that singularity problem is always there associated with this solution. But apart from that, we can get we can compute, we can calculate the temperature distribution using this particular equation. Now, this is the most important thing is that maybe if we assume the Rosenthal's 3D steady state equation and how to calculate the cooling rate and temperature gradient from the Rosenthal's 3D equation. So just here we have written the solution of the equation, heat conduction equation with particular assumptions, and T equal to T0 plus Q by twice pi Kr exponential minus V into R minus X by 2 into alpha. Here, one thing is that if we assuming the heat source is moving along the X direction. So once it is moving along the X axis, then del X by del T, partial derivative we are considering and keeping the other temperature as a constant. So del X by del T, we know that is that indicates the velocity value that equal to velocity V. That we normally use the dx by dt equal to velocity component. So that's why here we consider this as a V. Now I'm just focusing on along the X axis. Along the X axis at any point, definitely coordinate of Y and Z will be 0. And if you coordinate Y and Z equal to 0 and R equal to square root of x square plus y square plus z square, but x and y and z are 0. So basically R equal to x. So along the X axis. Now if R equal to x along the X axis, we can modify the equation T equal to T0 plus Q by twice pi Kr and e to the power 0, because here R equal to x. So e to the power 0 equal to 1. So you are getting basically T minus T0 equal to Q by twice pi K R. R equal to x here. So basically you are getting T minus T0 equal to Q by twice pi Kx. That is valid along the X axis. So along the X axis, we get the temperature distribution as a function of as a variable X. We can get it. Now, if we want to calculate the temperature gradient, so temperature gradient, you want to calculate that along the del T by del X temperature gradient. That is, we know temperature gradient means the temperature difference over the space. So basically dt, the temperature difference over the space dx. So dt by dx is basically indicate the temperature gradient. But in this case, del T by del X partial derivative we are considering because other variable we keep as a constant. So as a constant time, particular time, del T by del X indicates the temperature gradient. So that equal to, if you calculate T minus T0 equal to Q by twice pi X, I mean along the X axis, del T by del X equal to, if you do the first derivative of this equation Q by twice pi Kx, then you are getting minus Q by twice pi Kx square. Now you replace Q in terms of the T minus T0. So Q, replacing the Q in terms of the T minus T0 into twice pi Kx, that if you put it, then you are getting minus twice pi K T minus T0 square by Q. That is that you are getting the temperature gradient. Okay. Now, if del T by del X, now we are interested to know the cooling rate. Cooling rate means change of temperature with respect to change of time. So del T by del small t, that actually indicates the cooling rate. And if you use cooling rate over a particular point over a space, so del T by del small t over space X equal to the partial derivative we are considering this thing that is equivalent to del T by del X into del X by del small t. So that actually effectively del T by cooling rate. Now del T by del X, we have already calculated. In that case, the del T by del X is the temperature gradient. We calculate, we put this value, and del X by del T, that actually welding velocity, equivalent to the welding velocity. If you put it, then we are getting minus twice pi kV T minus T0 square by Q. These are the expressions. So this is the analytical solution of temperature distribution, assuming the Rosenthal 3D equation. Now, what inferences we can conclude from this particular expression, that we can see that cooling rate actually reduced significantly by the preheating. It means that T0 is basically reference T0 indicates the reference temperature, or maybe initial temperature, or maybe preheating temperature of the particular sample. I mean to say that when we're starting with the solution, we start from the one initial temperature, say in welding process, maybe it is in performing that performing the welding process at ambient temperature. So the initial temperature was the ambient. Now from the ambient temperature, raise the particular temperature. Now if it is preheating, means that already preheated, you already raised the temperature, and from there you are applying the heat flux, and then you are getting the solution of the temperature. So in that case, by modulating the T0 value, we can take care of the preheating effect in this particular equation. Now T0, if T0 is very high, then preheating is there, so T minus T0, the gap difference actually reduces. Once it reduces, means that cooling rate reduces if there is a significant amount of the preheating from this equation, keeping other parameters as a constant. At the same time, cooling rate decreases with increasing Q by V. If you from this equation, if we make it Q divided by V, that actually indicates the heat input per unit length, and that value, if the cooling rate decreases, if that value indicates the denominator value actually increases, then total value will be the decreases. So therefore, cooling rate decreases with increasing the Q by V value. That means heat input per unit length value, if you increase, then cooling rate can also be decreases. Third conclusion here is that temperature gradient decreases with increasing Q. Temperature gradient, we have already calculated del T by del X is the temperature gradient, and we can see that temperature gradient decreases with increasing Q. So here the equation, you can see the minus twice pi k T minus T0 square divided by Q. I'm talking about the magnitude, but neglecting the sign convention here. So basically, don't consider the sign, but just to consider the focus magnitude of this value. So Q increases, then temperature gradient also decreases. So this kind of the inferences we can derive from this particular expression. There is another part also, just to overall heat balance in a welding process, how to consider the different parameters. One is the arc power, how to calculate the arc power, that is equivalent to the arc voltage and the welding current. So multiplication of this, that indicates the arc power, that is in watt. And that is the directly measure the laser power, or maybe even for the arc also, the laser power or arc power. But in case of the laser, we directly measure the laser power. But in case of the arc welding, we measure the arc voltage and the arc current, and then we calculate the what is the arc power. Now we have to consider the efficiency also, because what are the heat is generated by the arc. All heat is not transferred to the workpiece. Some heat is losing because of the radiation and convection by from the once we creating the arc. So therefore, if we take care of this thing part, then we can introduce the efficiency term. So therefore, the net energy for the heating the workpiece, the once we creating the arc, the effective energy is transferred to the workpiece. That is the we introduce that Q equal to efficiency into Q0 term. Q0 is the actual arc power, and theta is basically indicates the weld thermal efficiency. So that's factor we have considered here, the weld thermal efficiency, that indicates the actual amount of the heat actually transferred to the workpiece. Now whatever energy is transferred to the workpiece, all energy is not utilized for the melting of the workpiece, because certain of the energy will be losing by the convection and radiation from the workpiece surface as well also. So here also we can introduce another efficiency term, that is called the melting efficiency. That is the Q1 by Q. Q is the actual energy transferred to the workpiece, and Q1 is actual energy utilized to melt the substrate. Now Q1 can be calculated like that. So we can assume that Q1 is responsible, the energy is responsible to raise the temperature from initial temperature to the melting point temperature. So that's the specific heat we can consider. And other cases, Cp into Tm minus T. Tm is the melting temperature, it is the initial temperature. So that to raise the temperature from initial to the melting point temperature. And then once in melting, there is a phase change from solid phase to liquid phase at the melting point temperature, that is called the latent heat. So then To melt, the specific heat and latent heat both are required to melt the substrate material. So that amount of the heat is basically utilizing for melting the workpiece substrate. So that's why this Q1 calculated Q1 by Q is basically indicates the melting efficiency. But Q1 is basically the total amount of the heat required to melt the oil metal up to the melting point, and that also includes the latent heat of fusion or basically phase change effect. But if you see the Q minus Q1, that is the amount of the heat, and that is consisting of the part of the liquid overheat, because in this case we are considering up to the melting point. We are not considering the overheating or superheating of the material, superheating of the liquid metal. So therefore that part, and along with the heat loss to the surroundings, that accounting equivalent to the Q minus Q1. So this is the overall energy balance once you look into very laser or the arc welding process. Now, if someone asks to say numerical, I just pick up one numericals and from some standard books available. Just look into the example. So we are considering the bead-on plate welding. That means there is not just simply hitting using the arc, simply hitting the substrate material of a thick steel plate is carried out using gas tungsten arc welding process, and that is the at 200 ampere 10 voltage, and the welding velocity, welding speed is 2 millimeter per second. Now, based on the Rosenthal's 3D equation, calculate the 500 degree centigrade cooling rates along the x-axis of the workpiece for 0 and 25 degree centigrade. Oh, sorry, it should be the 250 degree centigrade preheating. It must 0 and 250 degree centigrade preheating. The arc efficiency is 70% and the thermal conductivity is 35 watt per meter Kelvin. So these values are given. Now we try to solve this equation. What we understand from the Rosenthal's 3D equation. First, we along the x-axis. It's already say along the x-axis. Suppose workpiece is moving. So along the x-axis means y equal to z equal to 0, and we can calculate r equal to x. Therefore, we already calculate t minus t0 equal to q by twice pi kx. So that is the from here we can see put the values y equal to z equal to 0 and r equal to x in the Rosenthal's 3D equation. We are getting t minus t0 q by twice pi kx. K is the thermal conductivity and x is the variable. So therefore temperature gradient we can calculate del T by del X. Then that we account that Q by twice pi X minus twice pi K T minus T0 square by Q. This we have already calculated. Here you can see that temperature gradient minus twice pi K T minus T0 square by Q. So same thing we have written here. And from the application, we can see that del X by del T equal to V velocity. Now cooling rate del T by del T, one particular space, fixed space, the rate of cooling is equivalent to the del T by del X into del X by del T. And we can see that this equivalent to the twice pi kV T minus T0 square by Q. We have already seen that part here. Cooling rate we can calculate twice pi kV T minus T0 square by Q. Put this. Now there are two cases. One is the 0 preheating, another is the 250 degree centigrade preheating. Now here del T by del X we put this value. Just be careful the units and what are the numerical values we are putting. Of course, see twice pi K, the thermal conductivity unit of the thermal conductivity, watt per meter Kelvin or watt per meter degree centigrade, we put it. And then velocity in the SI unit 2 millimeter per second. Here we converted 2 into 10 to the minus 3 meter per second. And T minus T0. Here it's mentioned that calculate the 500 degree cooling rate. That means the at 500 degree what can be the cooling rate. So T variable is given. T variable is 500 degree centigrade minus T0. The 0 preheating. 0 preheating means that we are not preheating the sample, rather we keep in the ambient temperature. In that case, the preheating temperature is not exactly T0 may not be the 0. The T0 should be the ambient temperature. So that can be, you can assume it's a 25 degree centigrade. So that's why we have written 25 degree centigrade. T minus T0 square divided by Q. How to calculate the Q? 0.7 is the thermal efficiency into ampere into voltage. That once you calculate, you'll be getting the temperature cooling rate equal to 71 degree centigrade per second. Now, if it is preheating, that means already the initial temperature, not the ambient temperature, is preheated the sample. Similar calculation here, 500 degrees centigrade minus 250 degrees centigrade, because this is the preheated temperature. Got it? Then we're getting the 20 degrees centigrade per second. So we can see if there is a preheating, then we can see there is a decrement. That means cooling rate actually decreases. So that is the solution. So this kind of the inferences we can, or simple calculation we can perform using the Rosenthal 3D equation. Although nowadays the numerical solution also available, we can exactly see the more accurate result temperature distribution. We can be using any kind of the finite element based numerical techniques, but till analytical solution is valid to get a very quick solution, but approximate solution of an welding problem. I think that's all. This particular case. Now the second question is that why these advanced welding techniques are not being used in industries as similar to that of our conventional welding processes. Definitely, any welding processes, it is developed, it is being used by the industry only, but they are having specific application. Probably we have not seen the application. And once we see the, I have explained the several welding techniques associated with the laser and the advancement of the laser welding and laser micro welding specifically. And that micro welding process, it's anyway, it is used by the industry, but in a very micro scale process. And now this, if you the large scale in the industry specific, if you want to do the work on this thing, definitely each and every welding process having their unique advantage, disadvantage also. And of course, some welding techniques are material specific. One particular welding technique is very suitable, one particular material, and some other welding techniques may not be suitable in other kind of the different types of the material. So it depends on the specs. And certain cases, the choice of the welding process depends on the cost involved. For example, laser system is very costly, but as a substitute for the laser system, we can use the plasma arc welding process because the concentration of the arc is much more as compared to the other arc welding techniques in case of the plasma arc welding process. So therefore, sometimes plasma arc welding can be used as a substitute for the laser welding process also. So it depending upon the requirement and applications, all matters here also. And whatever welding techniques we have explained, each and every welding techniques are used in particular industry as per their requirement. Probably we have not seen or we have not observed the use of this particular welding process. But of course, if you ask why these welding processes, we can see even in construction side also. We can see that lots of welding is performed or joining is performed. And but if you want to do very high precision equipment, there is a joining process. Definitely, what kind of the welding process you have seen in the construction site, the same welding process is not applicable in a very high-end equipment when there is a requirement of the joint. There we need to lots of other welding techniques, lots of experiments to establish the welding process. For example, even aerospace industry, you can see the application of the welded joint also. Aerospace, but the material titanium, Inconel, they're having the unique problem, unique difficulties also they are associated with the. We cannot use any kind of the welding techniques for the Inconel. We cannot use any kind of the welding techniques for the titanium. Even depending upon the application, whether thickness of the sheet metal also, there is a application. For example, we have not seen the diffusion welding process, but diffusion welding is a well-established and very old welding techniques for the aerospace industry, and they're using for a quite long time this particular welding process. So it's our view what we are looking into the welding techniques and what we have seen this thing, the different applications of the different industry. It depends, entirely depends on that. I think that's all, and thank you for this for listening these particular slides. Now I like to say the few words also. In exam assignment, so you try to follow entirely the what kind of the problem is solved in the assignment. Try to follow that things, and the similar kind of the problem you can expect in the final exam also. So all the 2 marks, I think 2 marks questions will be there, and multiple choice type will be there, but some numerical problem will be there. So before You make a practice in the numerical problem at home also. Just look into the assignment problem. You are solving assignment problem, so similar kind of the problem you try to solve it, and of course strictly follow this the class notes or what we have shared or supposed to share the PPTs also. Just blindly follow the PPTs and nothing, no questions will be outside of this PPTs. Everything will be in this thing, but some cases numerical problem, you have to understand the concept. You have to apply the particular formula to a particular problem. That's all. But if you have any query related to the internet connection, this not able to register all this thing, this is not, this platform is not to discuss that things. So I cannot take care of all these things. I can take only the your any technical any queries related to the courses. I can answer you. That's all. Okay, I think able to listen me. I hope. And Sridhar, you have asked the questions, I think, and you also asked this question the Google this Google Sheet also. So one thing is that what exam format is the similar, what kind of the assignment it is there, the similar kind of the format will be there in the exam. First question. Second question is that there is no particular book I am following. There are so many books and I have listed down the references book in this thing. It's not like the kind of one book, everything is available. It's not like that. So you just, if you are interested in one specific area, specific subject, there are so many directions of this particular course also. Then you try to follow the textbook or what suggested books are there. I mentioned in the courses to follow that. These are the all very standard books. Otherwise, you have to, you make a very shortcut things. Then I think I can say the class notes or this what the notes is for that purpose you can utilize this. And if you have any query also you can raise your query. I hope it is okay. Sridhar, are you able to listen me? Okay, fine. If you do not have any other query, then I can stop here further. But anyway, if you have any query, you can communicate through your account through Gmail. I think through email also you can contact, you can communicate. Okay, so there is no other query. Now I can stop here. Maybe we can stop, close it.